Cool. So yeah, we're gonna get started. Let me get my screen share going. Shizota's still looking for team members. Thank you, Shizota. Great. Here's our notebook. Go ahead, open the notebook if you haven't already. But first, before we get into the notebook, that's right, it's time for a Kahoot. It was a hit last week. We're going to do it again. Put the PIN number, go to kahoot.com or open up the app if you have the app on your phone. Put in this PIN number. Once we have a critical mass, we'll get started. This is a Kahoot to review some of the concepts that we talked about last class around visualization. Can you guys see this Kahoot? There we go. We're good. We got 2 players. Oh, I got to get the music going. Here we go. The music's the best part. Just a little teaser of the music, maybe. Six players, 7 players. Eight players. We need more people. Jump in here. We got Kahoot itself is playing. Who was the winner? LeBron James is here. Who was the winner last time? I can't remember.
I think it was Sar.
Sar won. Nice, Sar. All right. See if Sar can defend his title, or maybe we'll have a new Kahoot champion. All right. You've got 1 more minute to join if you haven't joined already. We've got more than 13 people in the call. Give me some Kahoot hype. All right. I'm going to count down from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, we're going. 5 questions. They're going to go pretty quick. EDA stands for Electronic Dance Arts, Extra Data Analytics, Enter Data Architecture, Exploratory Data Analysis. What does EDA stand for? You've got 5 more seconds. I needed to put the timer on these fast. I couldn't tell if 20 or 10. What's the answer? Exploratory Data Analysis, Electronic Dance Arts, fooled one person. Exploratory data analysis, the process by which we kind of look into our data set, use some visualizations to get a feel for what's going on. That's what you guys will be doing on your project this week. Here's our leaderboard. Next question. What command would you use to make a graph that looks like this? Make sure you read them carefully. Timer's going fast. You got 4 seconds. Go ahead and answer. Hurry up and answer. Plot.bar. We tricked a couple people with pd.bar, but the command that the bar, or the package that the bar commands come from is plot. So good job. Get an update on our leaderboard. Quay is in the lead. Tyron and Brian. Don't know who is Brian. Don't know who that is, but we got our top 3. Lots of time for it to change, though. What command would you use to make this plot? What is that? I gave you 20 seconds for this one because this one's tricky. We've got some SNS options. We've got some plot options. We've got some mixes of some heat maps, some correlations. Most people got it. Good job. So this is the heat map plot, and we're calling it on df.corr. df.core returns the matrix of correlations for our data frame. And then the SNS heat map makes the heat map. So good job. You guys are killing it. Did our leaderboard change? Tyron is on his streak with 3 correct answers in a row. Marina, Brian close behind. See if they can catch up. What's a good way to explore the distribution of a single variable? Single variable being the keyword. Is it a histogram? Correlation heat map? We could print the values and read them. We could look at a scatter plot. It's a histogram. So scatter plot, a lot of people answered scatter plot. A scatter plot, you need 2 things to make it useful. So you could maybe argue with me, like you could look at a scatter plot of your variable with like time or something like that on the x-axis. But a scatter plot's useful for looking at how 2 variables are related. A histogram is the best way to visualize a single variable. What's our leaderboard doing? Oh, the top 3 don't change. We've got a steady 3 at the top. Tyron's running away with it. Anybody going to catch him? We've got one more question. What is the correlation of this variable? Take your best guess. There's a clear answer. What is if you calculated the correlation of the variables that were plotted in this scatter plot, what would you get? Good job. Most people got that one. And who is our winner? 3rd place, Marina. Very nice. Round of applause for Marina. Kahoot in 2nd place. And by quite a large margin, 5 out of 5, Tyron. Nicely done. Perfect score. Great. Thank you guys for playing. Any questions about some of those questions? Cool.
How'd you quickly identify the correlation in the last question?
Yeah, that's a good question. So the first thing you think about is, let me see if I can. I don't know if there's a quick way for me to get back to it. But the first thing you ask is whether it's a positive or a negative correlation. And so it had a pretty clear negative slope. So you know it's going to be a negative number. And then this is kind of a wishy-washy thing whether or not it's a strong or a weak correlation. So if you know it's negative, a negative 0.2 would be like you could almost barely even tell there was a pattern. Whereas in this one, it was very clear that everything was kind of in a band that really wasn't even that wide. So the negative 0.9 was the best guess because they were all actually pretty tightly clumped around a line together. Yeah.
All right. Thank you.
Cool. All right. We're going to get started with machine learning here. So, like I said, we're going to start with kind of like a high-level overview of what we're trying to do, and then we're going to have you work on building your first model yourself on this Titanic data set. So real quick, has everybody loaded this Jupyter notebook on their own computer? Go ahead and go. If you go to, if you pull from GitHub, there's this machine learning introduction and there's this Titanic example. Go ahead and open both. The Titanic example is where you'll end up writing a lot of your own code. I went ahead and gave you an extra place to do it so you wouldn't have to scroll up and down through all of our text. So are we getting some errors importing some things? I think I had to install this py.plus. So if you're getting an error importing py.plus, you can go ahead and comment that line out. We use that to make some visualizations, but I don't think you'll need it when you're running the notebook. And let me go ahead and do this too. So we've talked about Colab, and I linked a description of how to use Colab in Slack. But let me go ahead and take 5 minutes or so. Okay, that module too. You could also, I think, comment that line out too, sorry. But go ahead and watch how to use this Colab, because that's something that is a really nice workaround for if you're having trouble getting these notebooks to open. So if you just search for Google Colab, if you've never been there before, and open it, and log into your Google account if you need to log into it, you'll get a window that looks like this. And then you can upload from your computer, you can upload a notebook into Colab. And Colab is basically, it's like a Google Doc meets Jupyter Notebook. It's Jupyter Notebooks, but in the cloud on a virtual machine that Google provides for you. And one of the nice things about this is that they provide a virtual machine with a GPU that you're already able to work with without having to do anything in the back end. So if you end up doing something with deep learning, I'd highly recommend you do it in one of these Colab notebooks. The downside of doing this is that we have to like upload any files that we want to use. So like any CSVs or anything like that we're going to use, we have to upload here. But we can actually, I don't know if we've done this in a notebook yet, but you can use bash commands in a notebook if you append them with a exclamation point here. So we can clone into our GitHub. Another nice thing about this is just like a Google Doc, they're good for editing and collaborating with too. So when you're working on a project with a teammate, this would be another option. But I'm going to clone into the GitHub. I'm going to refresh over here on the side, and now I have all my 2020 spring data science files here as well. And I'm just going to pull out the Titanic. Will it let me drag it? I thought it was going to let me drag it. So you may have to change.
Would you actually recommend using Colab over notebooks?
I would recommend being familiar with both. It's definitely worthwhile to know how to use both of them. If you're just coding on your own computer, I would use a Jupyter Notebook, but the situations in which I would use a Colab are if I'm doing deep learning, if like right now something in your notebook isn't working and you just need to get it working really quick, or if you're collaborating with someone else and want to use this sort of like Google Doc-like interface, that's when I would use a Colab notebook. But for you guys who are having issues, if you don't want to, let's actually see if Colab has these. If you don't want, yeah, so Colab already has these models, these packages that you didn't have installed. Yeah, sorry, if you could, or whoever, sorry, I don't know who asked me that question. Okay, the echo is fixed. Thank you, Tyron. So yeah, this is a workaround for you guys who are having issues, so you don't have to wait for it to install the modules and things like that. The one thing to note is that you'll have to change the file paths. So this Titanic.csv will now be whatever the file path is. This, you have to put these folders in there. Great. So that's how to use a Colab, and that's a good workaround if you're not able to get those other notebooks going. All right, we're going to get started. So machine learning, big umbrella term that includes a lot of different techniques. But what we're trying to do is we're trying to take a data set. We're trying to learn the pattern that's in the data set, and then we're going to use the pattern we learned to predict new output for unseen examples. So you have a data set with a bunch of, we call them features. So we're going to start on this Titanic data set. This is what the Titanic data set looks like. The thing we're trying to predict is this survived variable. So that's going to be our output. We want to have some whole new rows that we've never seen before. We're going to put it into our machine learning model. It's going to look at the information in here, and it's going to make a prediction for whether or not that person survived. And these are what we call features. So the columns that aren't the label that we're predicting are features, and these are the inputs into our model that our model uses to predict our output. And this passenger ID is just a unique ID, so that's not going to be a feature. But for our features, we have our passenger class, so like upper class, middle class, lower class, their name, their sex, their age. This SIB-SP is siblings present. Is anybody frozen except for Gurjeet? Can you guys still hear me?
Yeah, I hear you.
All right, cool. So the siblings present is the number of siblings on the boat with the person. This part is the number of parents or children on the boat, their ticket number, how much they paid for their fare, their cabin number, and then this is a port that they embarked from, and I don't actually know what those stand for. And there's a bunch of like benchmark data sets that people use to try out new algorithms on or to practice on and things like that. So this is a classic benchmark. This is what we're going to be using. So from a high level, there's a couple types of ways to group machine learning problem or machine learning algorithms. And the first one is regression problems versus classification problems. And it's really simple. In a regression problem, the output that we're predicting is continuous. So this could be like predicting housing prices, predicting like a stock market value. You're predicting continuous values. And so that's a regression problem. Whereas in a classification problem, the rows, the outputs that you're trying to predict are labels. So you could be, in this case, predicting whether they survived or didn't survive. You could also be predicting, I'm trying to think of an example. If you were predicting like flower species based on the image of a flower, that would be a classification problem. So drop in the chat on this Titanic problem that we're going to be tackling. Is this a regression problem or a classification problem? Is this Titanic a regression or a classification problem? We've got to vote for regression. We've got to vote for classification. Who's going to break the tie? Classification, another vote for classification. Anybody else want to chime in? Mike says classification. Tyron, we're trying to predict whether or not a one of these passengers survived the sinking of the Titanic. So we're trying to predict whether or not this is a 0 or a 1. So good. So everybody's on board with classification. You could think maybe it's a regression because we're predicting a number here. But these numbers are just labels. 0 means did not survive and 1 means survived. So this is definitely a classification problem. So the models that we're actually training, so what it means to train a model is first we have to have data, and we have to have a lot of data. So we're usually talking, it depends a lot on the exact model. We're going to say at least a couple hundred rows in your data set to be able to build a model. When you're talking about deep learning, you need like hundreds of thousands, if not millions of instances in your data set to do your learning on. And so our Titanic data set has, I think, like a little under 800 or a little over 800. But really, like in the thousands is the amount of data you want to have to feed into your model. And you feed it into your model looks at all this data, and then it's adjusting some of its own internal parameters based on the data to be able to make predictions. So a good example of this is regression. That's kind of a simple model for making predictions that a lot of people are familiar with. And it's just assuming that there's a linear relationship between the output that you're trying to predict. So that's the y here. So you can see the y on the y-axis. This y hat is what we're trying to predict. And your features are your explanatory variables, which are the input to the model. So in this super simple case, we only have one input. We have one x. That x gets multiplied by a weight and then gets added to another weight, and that gives us our prediction. So wherever this x is on the line, that x gets plugged into your classic y equals mx plus b that you remember from high school algebra, and then whatever the output is your prediction. And so when we talk about a model learning, what we're talking about is just the algorithm deciding what these weights should be. And there's a couple different ways to do that. We're not going to go into it right now. We're going to cover actually regression problems next week. We're focusing on classification this week. But that's just to give you an idea that when we're talking about the machine learning from the data. What we're actually talking about is just the algorithm figuring out what this W0 and this W1 should be. So we have this distinction between regression and classification, and they need different different algorithms to be able to differentiate between these two tests. So this is a good example of what those different algorithms can look like. So we have linear regression here. This is for a regression problem. If we want to use the sort of same regression framework to do a classification problem, we use this sigmoid function instead of a linear function. And the sigmoid function here we use because it's got this nice curve where it can differentiate between like our positive values up here and our negative values down here. So that's just to give you a sense of how the algorithms change when we're doing classification. So the way the classification would work is we would feed it into this. This is called logistic regression with this sigmoid. And if the value is above the threshold, we would return a 1. If it's below the threshold, we would return a 0. So that's kind of a way to turn a regression algorithm into a classification algorithm, is to set a threshold. Anything above the threshold, we turn into a 1. Anything below the threshold, we turn into a 0. So that's just to give you kind of some intuition about what's happening. We'll go into more detail about exactly how these models work later. So we can separate between regression and classification. We can also separate between supervised and unsupervised. And supervised just means that we have a data set that includes the labels. Unsupervised means we have a data set with no labels. And it's a good question if you ask yourself, well, what can we do if we don't have any labels? And usually it involves something like clustering the data. So even if we don't have labels, we can cluster things together. So ReLU function instead of a sigmoid. ReLU is a little bit different than a sigmoid. You could definitely you could still set a threshold for your ReLU. But yeah, ReLUs are kind of a whole separate thing related to deep learning that we might get to hopefully later in the semester. So supervised learning, we have labels. Unsupervised learning, we don't have labels. Maybe we're clustering. Another example of unsupervised learning is trying to reduce your number of features. So you combine your features and transform them in some way so that you have less features. You can also do reinforcement learning. What kind of learning are we doing on this Titanic data set? Supervised, unsupervised, or something else? Drop it in the chat. Let me know what you think. Are we doing supervised? Are we doing unsupervised? Supervised question mark, says Noor. Supervised, supervised. So you guys are right. We have our labels in our model. Our labels are this survived column. We know whether or not people survived. What we're trying to do is train on this data set so that we can predict passengers who we don't know whether or not they survived. An example of unsupervised would be, let me think for a second. So clustering is a great example. I'm just trying to think of a good example of when you would want to cluster. Let's say you've got a bunch of stock prices along with some other information about a company, like how many employees they have, their stock history, how old they are, things like that. You can put all that into a model that will just group the companies based on these characteristics. So maybe you would have a group of really large companies that had been around for a long time. Maybe you would have a group of companies with a high stock price who haven't been around for a long time, who are like just emerging to the scene, stuff like that. And we'll talk about clustering models another time. So training a model. So first of all, you'll notice at the top, we imported a bunch of things from this sklearn, scikit-learn package. So scikit-learn's great package for doing machine learning. And they make training the model actually super straightforward. So the package has abstracted away everything we need to do to train a model. And we do it in 2 steps. The first thing we do is we initiate our model object. And so I called it model. Some people call it classifier. Some people call it CLF, abbreviated classifier, things like that. So we're going to initiate our module, and we're going to set it equal to this function call of the type of module we want. So we're going to start with the logistic regression module, or sorry, logistic regression model. But there's other models out there. We could do a decision tree right here. But we're making this function call that we imported from the scikit-learn library. And there are some options here. So any of the options that you put in when you're first making this call are called hyperparameters. And the exact values you put in there for the hyperparameters is the subject of a lot of research and people thinking really hard about and things like that. But they're set up pretty good so that the default arguments will be good for us. So when we run this, we have whatever this scikit-learn returns when we call logistic regression is now stored in our model. And model has a bunch of methods and things like that that we're able to call. Now what we need to do is we're going to call one of the methods that our model has is this fit method. And the fit method is what it uses to actually fit itself, to train itself to the data. So this fit method is what the model's doing to learn, if it was a regression model, like what these weights should be. So the fit model is how we actually train it. To fit our model, we need to feed it our features and our labels. So our features go first. So our features here are just the columns that we're predicting from. So it's all the columns in our data frame minus survived. This is very important that when you're feeding the data into your model to train it, you do not put the label here. So if we included survived in this first column, what's the problem with that? Do you guys have an intuition for why we can't include survived in the data frame of features that we're feeding into it? North says creates a bias. That's not, you're kind of along the right track. Yeah, so survived is what we're trying to predict. So if we included that in there, all it would do is it would look at the survived column and it would say, okay, is the survived column a 0 or 1? And then that would be whatever its prediction was. Does that make sense? So it's good to be careful about this. Sometimes you make mistakes, and sometimes it's less obvious than this. Sometimes you have information bleeding into your predictor that you don't want to be getting into your predictor. So it's an important thing to watch out for. But when we're fitting our model, we first pass our features, then we pass our label. But when we run this, so this is a negative example. This is an example of what you shouldn't do. We get an error like you can see, and our error is could not convert string to float. And so what's happening here is scikit-learn abstracts a lot of this away in this fit method and in this logistic regression function, but we still need to do some work to actually transform the data that we have to get it into a form that our model can use. And so as you can see here, our model can't use strings. It doesn't know what to do with strings. So one of the things we need to do is convert all of our strings to numbers. And we'll talk about other ways to convert our features too. But this whole general process is called feature engineering. So that's a good phrase. And feature engineering is like the bulk of the work that we'll actually have to do when we're training our models. Because smart people have made these packages that we can use that do all the work of actually fitting the models and figuring out what the weight should be and things like that. And so our job is to figure out how to engineer these features to get the best performance out of our models. So let's see how we do that on the Titanic data set. So first of all, what columns can we use without any transformations? So of these columns here, let me know in the chat, which ones can we just put directly into our model without even worrying about doing any sort of transformation into them?
The fair.
So we can put the fair, good. The fair is just a number, so our model should be able to handle that. These are just numbers. What else?
Age.
Age, yeah. Siblings, parents,
Passenger
child.
ID, survive, P class.
Perfect. We're not putting passenger ID because that's just an ID, but you're right that we could if we wanted to. So these are the features here that we don't have to transform at all. These are the ones you guys just listed. And these are just the ones that are numbers and not strings. And so we also can't have, it depends on the exact package, but for scikit-learn, you also can't have null values. in your columns. So what I did here is these are our features. For each of these features, I just printed the number of null values that it has, and you can see everything's good except for age. So if we fed age into our model without doing anything with those null values, it would also give us an error. So I kicked age out of the list, and now we've got a list of these 4 features here. And let's see what happens if we try to fit our model. So we get an output, we get this warning that we can ignore. And it looks like we don't have any output, right? So we fit our model, it successfully ran, and we get this kind of cryptic message here that just says logistic regression and tells us a bunch of arguments here. So this is kind of a confusing part about it is our model did fit. It actually successfully updated those weights for our data set, and it's ready to make predictions. And it's all stored in this model object. So to actually get at what it did, let me actually show you real quick. So we can make a prediction if we do model.predict. Let's do... So I'm just getting... I hope this works. The first row... Oh, it didn't work. Okay. I'll just do the whole thing. So we can use this predict method, and we'll put in the features, and it'll tell us its guesses for whether or not that passenger survived. So now that we've trained our model, we want to know how we did. We want to like test it out on some new data to see if it's, is it just as good as if we randomly guess zeros and ones? Has it actually learned something? Things like that. But we've made a big mistake, which is that we trained our model on the whole data set, and now we don't have any data left over to kind of test it out on. Does that make sense? So what we need to do is this train test split. And this is probably the most important thing we'll talk about here. And this is the whole paradigm we use in machine learning to be able to successfully evaluate our models. And the idea here is that we're going to withhold some of our data, which feels bad because we just talked about how you need a lot of data to be successful in machine learning. And usually the more data you can throw into an algorithm, it'll get better. So it feels bad to not use all the data that you have. But what it does is it allows us to actually have a sense of how our model is performing. So it lets us do a couple things. It lets us see how our model is generalizing to new unseen data, which is really important. And it also lets us compare between different models, or between, like if I did some work and Carlos did some work and we wanted to see whose model was doing a better job of predicting, we could both test our model on a test set and see who did better on the test set. So we're going to, at the very beginning of the process, we're going to split our data into train data and test data. We're going to train only on the train data, and then we're going to make predictions on the test data and see how those predictions match up to the actual values. So that's kind of the paradigm for how this whole process works. Is you split it, you train on the train data, you test it out on the test data, and then you can go in and make changes. And if your model does better on the test data, you know that those changes were successful. So to actually to split our data into train and test, we have this handy function from scikit-learn called train test split. And I literally always get confused about this. So in the train test split, we feed our features data frame, our labels, our test sizes, what portion of the data we want to be in our test set. So we're doing 20% of the data in a test set, and 20% is like a standard value. And then this random state, anytime you have a function that relies on something random, you can set this random state as like a seed for that random process so that other people are able to recreate it. So I did that here. It's not necessary, but that way you guys can have the same split at home. And then this is the part that's always hard for me to remember, but you do your train features, then your test features, then your train labels, then your test labels. So this is like in Python, we're just assigning 4 things at once. So this is assigning everything here. A lot of times you'll see other people call this X train, X test, Y train, Y test, the idea being that your X is the features and your Y is the output you're trying to predict. I labeled it features and labels to hopefully be a little bit more intuitive. And then we did a quick test here to make sure that we had 891 examples at the beginning. In our train data set, we have 712. In our test data set, we have 179. And those do add up to 891, so it looked like it worked. And if we go in here and look at our labels and our features, we can see it's just another pandas data frame, but it's been split up. So that's great. So now we're doing the same thing we did before. We have our logistic regression model. I keep saying module instead of model. An important thing here is anytime you're starting a new model, it's important to call this line here to kind of reinitialize it. It's a little confusing, but basically, if you didn't reinitialize it, it could like keep information from the last time you trained it, which is what we don't want. So this line like resets our model. This line fits it. And then we can predict this. We can predict one value. We can predict a lot of values. But now, if we do model.predict on our test data set, which is called test features, we get all these values, and we want to know how we did. So we want to evaluate our model's success. The most important thing we're interested in is our accuracy. So that's just a measure of what percent of the test data set that our model got right. So it's literally just the number of examples it got right divided by the total number of examples. And we can do this using accuracy score. It's important you feed the ground truth in first. So our test labels is the correct values. Our model.predict test features is our predictions. And this will tell us we got a 70% accuracy. So 70%, that seems pretty good. We can pat ourselves on the back. We hardly did any work. All we did was limit our model to those features that we didn't have to do any transformations to, and we already got 70%, so that's sweet. But you have to be careful about interpreting this accuracy number. One of the things that can happen, so if we fed more data into the model, that number would probably go up. But an important thing to keep in mind is the baseline accuracy. And what I mean by baseline accuracy is that if you just, so we don't have a perfect split between survived and not survived. You can see that 60% of our test data set is zeros. And so the baseline accuracy here is actually 60%. If you just trained a stupid model to only guess 0, it could get an accuracy of 60%. And this is important in examples, like especially medical examples. If you have someone who's trying to like detect the instance of a disease or something like that, but like if only 1% of the test set has the disease, they might report like a 99.2% accuracy, and you're like, holy shit, a 99.2% accuracy, that's incredible. But the baseline accuracy is already 99% if you just guess that every single person didn't have the disease. So it's important to keep this baseline accuracy concept in mind when interpreting these accuracies. So that was our first model. We didn't do any feature engineering. Now let's go back and let's actually take a closer look at our features and see how we can improve on this 70%. So I did a couple of things here. I grouped the data frame by the class, and then I looked at the mean of the survived column to get a sense of how class influences whether or not people survived. And you can see if you've got a high class, so this is like an upper class person, you're much more likely to survive than if you were a lower class person, which makes some intuitive sense. You can also see the same thing here, that women are much more likely to survive than men. This one I did opposite. You can't group by age since it's, there's like 60 unique values or whatever. But I grouped by survived and took the mean of the ages. And so the people that didn't survive and the people that did survive have about the same age. So it looks to me like, oh, maybe age isn't the best predictor. Same thing down here. It's hard to interpret this siblings present column, partially because I think some of these values, there might only be 1 or 2 people that had 8 siblings present, same with 5, and they just didn't happen to survive, which kind of skews how we can interpret this. we can look if you have one sibling, you were more likely to survive than if you had 0 siblings. So that's interesting. We'll keep that in our back pocket for later. Same thing for parents. And then I did the same thing for fare that I did for ages. So it looks like maybe if you paid a higher fare, you're more likely to survive. But that could also just be another indicator of class. If you paid a higher fare, it might be that you're a higher class. So we're going to start, instead of throwing all those models in there, all those features into our model, let's just start with sex and class and see what we're able to do. So the first thing we need to do is we need to change our sex column to 0s and 1s, because remember, we can't take strings. And then our features are only going to be class and sex. Here we're doing our train test split. We're reinitializing our model, which we have to do. We're fitting our model to the train features and the train labels. Notice here that I did the train test split on DF features and DF survive. So this DF features took only class and sex, and that generated this train test split. Then I initialized the model, I fit it, and I'm calling this accuracy score function on the actual labels and our predicted labels to see how we did. And we did a lot better. We got 70% before, now we have 79%. So we got a 10-point increase. We actually used less features, but we included sex, which we didn't include before, and we took out some of those things that we thought maybe weren't highly correlated and things like that. Great question, Tyron. See how much each feature contributes to the score. There is, I'm going to have to look it up though. And it depends on the model too, but the logistic regression, remember that what it is it, so first of all, scikit-learn has great documentation. Best place to go whenever you're trying to find something like this out. So I think it's this get params is what we want here. So this get params is a method on our model that'll tell us our parameters. Maybe that wasn't what I wanted. I'll have to look this up. I'll look this up while you guys are working, and I'll get back to you.
Steve?
Go for it, Carlos.
I think you can try it using decision tree if you after you train it and then you do feature importance.
Yeah, that's for a decision tree. Do you know if you can how to look at the weights for logistic regression? I was thinking we could just look at the weights, but like I said, I'll look it up real quick while you guys are working. So I'm about to turn it over to you guys. So open up that Titanic example notebook. And what we're going to do is we're going to have you guys train a model from beginning to end. I did a couple things for you. I loaded the data into the DF data frame. I renamed the columns, and I did that same mapping for the sex column. And so what I want you guys to do is to, just like we did here, where we were able to get an increase in our test accuracy by doing a little bit of feature engineering, by including this sex column, by dropping some of the other stuff. I want you to do one of these feature engineerings I listed here, and then do the train test split, fit the model, evaluate your results, and then we'll come back together and we'll see what people tried that were able to get better results. So some things you could try. You could look at these siblings present and this parent and children present variables, I think would be very helpful to this. But like we said, we need to maybe do a little bit of transformation to solve the problem that, you could just throw it in there and see what happens actually. Or you could do some transformations to look at whether or not the passenger is alone. So you can make a new column called like is alone or something like that, that has a 0 if the passenger is alone and a 1 if the passenger is not alone. Nor just comment out the line that's importing PyDat plus. You won't need it in yours. So you could create this new is alone column, feed that into the model, see if that works. We could use the name column as something we haven't considered. And one way to use the name column is to extract the title. So we've got a Mr., we've got a Mrs., we've got a Miss, we've got a Mrs., we've got a Mr. Maybe those titles influence whether or not the person survived. It's worth trying. Remember, we didn't use the age column because it had some nans in there. You can fill the nans, and I don't think we've talked about this, but there's a method called fill in A, I think it is. Yeah, so you can do df.fill in A, and it'll fill all the nans with whatever you choose. So you could just fill them with the average age. You could do the median age. You could do something a little bit fancy and try to predict the age. You could look at the embarked variable, and you could one-hot encode the embarked variable. I'll let you guys look up what one-hot encode means. And then forget about the last one. I don't know if that would actually work. You could look at the map of the Titanic and see if you could use the cabin information, but that'll take too much time anyways. So pick one of these 4 things you think will be successful. Open up this notebook, do the data transformation, do the train chest split, the fitting, and the scores, and then we'll come back together and we'll see how you did. And please let us know if you have any questions while you're doing that. I can kind of start coding one of these, so if you're kind of stuck, you can at least follow along with what I'm doing. And yeah, let's say 10 or 15 minutes. We'll see where we're at, and then we'll come back together. Does everybody understand what's being asked of them? So the task, Nassan, is to go in this Titanic example notebook. Actually, let me enter Sujata real quick. So Parch is the number of parents and children. So you have the number of siblings and the number of parents or children. So Nassan, the task is to build your own model on this Titanic data set. And it's in, let me share my screen. Yeah, no worries if you were fixing yours. So open up this Titanic example notebook. Do one of these things to change the features. And then I want you to yourself do the train test split we talked about, fit the model that we talked about, and then report. We haven't talked about recall or precision yet, but report the accuracy score. And see, I'm interested to see if you can beat our score of 0.793. Any questions so far? How are people doing? All right, SAR's pretty lost. Okay, let's see. I can walk through some of this together. So let's see which one of these I want to do. So let me start sharing. All right, so our first task is to make some more changes to our data frame. So I suggested a couple of things here. Let's actually look at the embark variable, because then we can talk about one-hot encoding. So if we look at our data frame again, oh, I actually didn't run this stuff. So when we did class and sex, we did pretty good. It looked like embarked, maybe influence. Let's look at that again. So if you embarked from this C port, you had seems like a pretty significantly higher chance of embarking, or sorry, of surviving than if you embarked from this Q or this S. And that could be that, you know, maybe people were on different parts of the ship depending on what port they got on the ship on. And then so if they were on like a better part of the ship, maybe they survived. I don't know, but it seems like there's a difference here. It could also be related to class again. So what we're going to do is we want to use this embarked variable in our model. And so to do that, we need to do something. So one thing we could do is we could just map these values to numbers. So we could be like, okay, let's say C is equal to 0, Q is equal to 1, and S is equal to 2. But then we're kind of artificially incorporating some ordering. Does that make sense? So it's okay for our class variable to be a 1, a 2, and a 3 because the ordering actually kind of makes sense. But with this embarked, I'm a little bit nervous about just kind of turning them into numbers like that. So what we're going to do is instead we're going to use this thing called one-hot encoding. And let me just look up. Need to remember. Yeah, we'll just do. So one-hot encoding means we're taking this variable and we're going to turn it into a series of columns with zeros and ones for whether or not they embarked from these ports. So we'll have a like embarked from C column with a 0 or a 1 for if that row embarked from C. We'll have an embarked from Q column with a 0 or a 1 for if that row embarked from Q, and then we'll have an S column too. So to do that, we do pd.getDummies on df.embarked. And let's see what we get out of that. So you can see it gave us this new data frame with a C, a Q, and an S column, and there should be only one in each of these rows, and it's telling us which port it embarked from. So now we can get this information into our machine learning model but we need to combine this back into our other data frame. So we're going to do df.join. And now we have our old data frame back. And at the end here, we have this C column, this Q column, and this S column. So let's set this equal to df. And then now you can just, I was thinking you guys could just go back here and just copy what I did here. So we got to do the train test split. So we'll do that down here. So we got train features, train labels, test labels, train test split, df features. But our features are now, we're still going to use our class and our sex, but now we want to use those other columns. So it was C, Q, and S, I think. Let's double check just to be sure. Yeah, C, Q, and S. So now our new features are class, sex, and then these dummy variables for where they embarked from. We've got our train test split, looks good. We don't need to change anything about that. Our model, we can try a different model. Decision tree classifier is one of the models we imported at the top. You can look at the list of models here to pick one out to try. You've got logistic regression, random forest, k-neighbors, decision tree, SVC, voting. Don't use voting classifier yet. And I'm not expecting you to know what these are other than that they're all models that we can call just like we call here. So we've got our model initialized. We do our model.fit, and we're going to do it on our train features and our train labels. And then we do see how our model, let's just fit it first. So it spits out that it made a decision tree classifier for us. That's great. And now we're going to do accuracy score, test labels, model.predict, test features. And look at that. We got a little bit of an improvement. So we were at 79 before. Actually, we changed two things. We changed our model and we changed some of our features. So it's hard to tell what we got an improvement from. Let's put this back to logistic regression real quick. That's what gave us our 79. Oh, okay. So our model. So when we added these features to our logistic regression model, our accuracy score went down. Let me just see what this does if I get rid of that S. No, that didn't do anything. But by doing this mix of adding features and switching to a decision tree, we were able to see a small jump in our improvement here. And so that's kind of the whole game is you get a model started, you see what kind of accuracy you get, and then you say, okay, like what's going to happen if I try this model? What's going to happen if I make this little change to the feature engineering? You make that change, you run it again, you see how your accuracy score looks. And if you had a little increase in your accuracy, then you're like, cool, seems like that worked. And then you move on to another thing. So there's like a fun little give and take here around testing. But like Shizota just said, what does it mean if it goes up in one and goes down in the other model? I'm actually not sure how to interpret that. And so it's not entirely scientific. It takes a little bit of practice to kind of be able to interpret these results. But to get you guys started, the idea here is to come up with a change, make a change, and then see what kind of change you get on your accuracy score. And yeah, I don't know why you would think if you're adding more data, it would be hard for it to go down. But I think the idea is that this decision tree, we'll talk about how decision trees work, but it might not end up using all the features, whereas a logistic regression, it multiplies every single feature by a weight. And so it's possible that by introducing these zeros and ones, I think what happened is it kind of took away from the importance of the class and the sex. I think the class and the sex are still much more important than where you embarked from is. And so by introducing these less important things, we're kind of like confusing the weights a little bit. That's kind of my like hand wavy guess at why it went down. Does that make a little bit more sense of what was being asked of you guys? Or are we still a little confused? If we're confused, let me know what you're confused about, Sar and Nora, and I'm happy to answer some questions. 96% accuracy. Can you share, Tyron, can you post the screenshot in Slack of what you did? That's pretty high. That's super good. I don't think I've ever gotten 96 on Titanic dataset. Yeah, Tyron's got some insider info. That sounds right. But yeah, Tyron, post what you did in Slack. I'd love to see it. Was anybody else able to actually get a model up and running? Let's see real quick how our decision tree does on just these two variables. Okay, so our decision tree on these two variables actually did worse than. What are the errors you're getting? Sorry. So you need to do this one up here, df equals df.join this pd.getDummies df.embarked. I'm going to take a look at what Tyron did. Random forest. Sweet. This is nuts. So Tyron, I want you to change that random state. You can actually just take it out and run it a couple times. And each time you run it, it'll have a slightly different test set and see if your other accuracy is as high as that first one is. But nicely done. So did everybody see? So Tyron went with the using the age, included the age in his features, and looks like also just straight up included the number of siblings and parents present and the fair, and didn't include sex, and used a model called a random forest classifier, which is a good model to use, and was able to get 96% accuracy. So they're switching between 92 and 97. That's still super high. Well done. So any other questions about this kind of general sort of framework for how we're doing this train test split and then what we're looking at after we train a model? Do you guys want a little bit more time to try to make your own changes to the features? Let me know in the chat if you're working on it and want some more time, or if you're still kind of confused and are ready to move on as a group. So we need to split into a train and a test set so that we have a test set that we're able to evaluate our model on. And it's a little confusing because it's split on two lines here for readability. But what's happening is we're using this train test split function that we imported from scikit-learn. We're using this train test split function, and it takes it has to have two arguments. The first one is your features. The second one is your labels. So the things you're splitting, and they need to be separated into features and labels. This df features is subsetting our data frame on these features columns. And these are our features columns here. So this df features, let me just show you. df features is just this data frame here with these 5 columns. df.survived is just the string of zeros and ones with the labels. Test size is the proportion of our whole data frame that we want to be in our test set. So we're going to have 80% in our train set, 20% in our test set. Random state is not necessary, but it's there so that we can have the same train and test set if we want. So this could be any random number here, and it's just a way to recreate things. This function returns 4 things, and it's important that the order it returns them in is right. So it returns a new data frame that's 80% of the old data frame with the features, a new data frame that's 20% of the old data frame with the features. So we called that our train features and our test features. A new data frame of just the survived that's 80% of this, and then a new data frame of just survived that's 20% of it. So that's our train labels and our test labels. And then those are what we use to fit our model and then make predictions. So let me know if that cleared some things up or if you still have questions. When I do df.join, I get a value error, columns overlap. I don't know what's causing that. Let me try. I think if you run df join, yeah. So if you only need to run it twice. Yeah. You only need to run it once. If you run it twice, you're going to get that error. So it looks like, go ahead and look at your df. And maybe I didn't write that the best way. But print your df to the console, just call df and see if it's got those things at the back.
Also, Steve, another thing you can do using the get dummies is that instead of joining, you just pass home the whole data frame and then specify which columns you want to get the dummies from.
Oh, nice. I don't think I knew that. That's a really good call. So you're saying pd.getDummies,
just df,
comma,
columns,
and then use. Okay, sweet. That's good to know. Yeah, so columns equals sweet. Good tips, good tips. Wow, look at that, everybody. Carlos with the pro tip. So that's a much better way of doing it than what I was doing, where I was joining back onto the original data frame. So if you didn't hear them, you call get dummies, you pass the data frame, and then you specify the columns you want to get the data frame on. So that's a much better way to do it. And it looks like it replaces that embarked column, and then it has a nice name here. So if you do that, you'll have to change this to embarked C, embarked Q, embarked S. Let me know where you guys are at. Are people still working on... No, that didn't work. Are people still working on making some changes? Yeah, sorry, that's exactly right. That is exactly right. Accuracy score, good question. We imported from scikit-learn right here. It's not a complicated one. You could write that yourself really quickly. It's just comparing at each index to see if they're the same. Do you guys want to do another example? Let's do this age one since that seemed to work well for Tyron. So we're going to say, I need to look up this. So Sarah asks, should we look for a data set that we would like to predict using some data? Yeah, that would be a great way to find a data set, is to think of something you'd like to predict. So some people have talked about predicting like housing prices because of the recession. So you could look for a data set that has like lines that has like a sale value for a property along with some characteristics of the property and like a date and things like that. And then what you're doing is you're putting those characteristics of a property into your model to see how it predicts what the price will be. So yeah, anything that you're looking to predict where you have a data set, it's important that it has the labels, remember, and it has some features that it would make sense to predict it by. Anything like that would be a great project idea. Oh, did I freeze? Can you guys see me? So let's do this age thing real quick just to get some more practice, and then we'll move on unless people tell me they need more time. So I actually need to look up this fill NA. Remember how it works. Oops. How do you tell it what values to? Okay. So we're just going to do df age equals df age fill in a mean df age. I think that'll work. Oops. Oh no. So it's going to tell me, yeah, I just filled my data frame with a method, which is kind of funny. Okay, cool. So now we don't have any NAND. So all I did was I set the age equal to the age column, filled all the NAND values, and the value I filled them with was the mean of the column. So hopefully that makes sense. And now I'm going to throw age into my features as well. It's because I didn't run this. And we got like a 2% bump in accuracy by including the age. So that's great. Still weren't able to meet Tyron's score, but kind of gives you an idea of how this goes. All right, let me know if you're still working, if you have any questions. I'm going to talk for just a second longer, and then we're going to take a break. Cool. We're going to move on. So really quick, some other ways to evaluate your model other than accuracy. Accuracy is an important one, but there's some other important ones too. And I think I'm just going to very briefly touch on these and then have you guys read about them on your own time. And then we're going to go to a break, and Carlos is going to take over. Mike says, question about the project, will it be geared more towards predictive models? You can take your project a couple different directions. We want you to have something visual that comes out of your project at the end, because that's what'll be like a really snappy thing to present to people. So if you do a predictive model, that would be a really great thing to do. You can use these methods we're talking about on a new data set, trying to predict something you're interested in. And then I think we would want you to either make some visualizations describing like the process you use to make your model, or ideally put your model online and have like an interface where someone can input their own, like if you're predicting housing prices, someone can input their own neighborhood characteristics or whatever and get a prediction, out of your model. Just because that's like a nice thing to be able to show off, and it won't be, once you build your model, we'll show you it's easy to load it in whatever web framework you're using and kind of make a very simple interface around it. So that's kind of one option. The other option is you don't have to do any predictive modeling at all if you don't want to, and you could make sort of like an interactive data visualization on a data set you're interested in. And instead of doing the predictive modeling, you could spend a little bit more time making the visualization look nice and adding some interactive elements like some sliders and some things like that. Those were the two general directions we had kind of outlined for the project, but if you've got other ideas, we are always happy to hear some new ideas. So other evaluation metrics other than accuracy that we can use. So the first thing is we can look at this confusion matrix. And what this confusion matrix does is it gives us a matrix. Can I make it bigger? All right, so you can see it up here. So this always happens to me with confusion matrices, is that these positive and negative values are sometimes switched to what you're getting out of scikit-learn. But the idea is that you have your actual values and your predicted values. And you have 4 options here. If it was actually a 1 and you predicted it to be a 1, that's the number in this column. If it was actually a 0, but you predicted it to be a 1, so that's like a false positive. It was actually negative, but you predicted it to be positive. That's up here. You can have false negatives, and then you have your true negatives down here. So a confusion matrix divides up the different errors you're making. And you can see, so we had 107 true positives. So true positives is going across the top here, or actually it was zeros. So it is reversed from that picture. So we had 107 zeros. So out of all those zeros, we correctly predicted 106 of them, and we only got 1 wrong. So that's pretty nice. But notice of our ones, so of our people that survived, there were 72 of them. Our accuracy rate on the people that survived is less than half. So our model is actually pretty skewed. It's predicting a lot of negatives, and it's missing a lot of the positives. So we predicted 37 people to die who actually survived. We correctly predicted 35 people who survived, and then there's 1 person who we predicted that they survived and they actually died. So that confusion matrix kind of sums up all of the mistakes you're making. And then precision and recall, I'll have you guys read about on your own time. But precision is so it's of the things that you predict are positive, it's how many of them are actually positive. So it's like so recall, I'll actually start with recall, that's more intuitive. Recall is out of all the positive examples, how many did you get? So it's how good your model is at picking out the positive examples. So you take, and you can see these nice little illustrations down here. So you take your true positives out of your total positives, which is this half of the diagram, and that gives you your recall. And then how many selected items are relevant, that's what I was trying to say, that's a good way to put it, is precision. So it's out of the items that you selected, how many of them are right. So in ours, we're going to have a high precision because out of the ones we predicted survived, only 1 of them was wrong. So our precision's at 0.97, but our recall is very low. Out of the ones that survived, we were only able to get 35 of them, and we missed these 37. So you can see our recall is just under half. So I'll let you read more about that on your own time and think about why there's a trade-off between precision and recall here. The last thing is that you can make a curve showing how these false positive rates and true positive rates relate to each other. And if you calculate the area under your curve, you get your ROC, area under the curve, which is abbreviated ROC AUC. Don't worry about that too much right now. I just wanted to point that out, that was out there as another metric that people use for evaluating classifiers. We're going to take a break. So let's come back, and I'm going to say 5 minutes, get some water, take a break. When we come back, we'll talk about overfitting and underfitting. We'll talk about exactly how these models that we're using are working. I'll see you guys in 5 minutes.
Okay, so we're about to start now. Just 1 more minute. Sure. I mean, like this notebook or this one here? This one? Okay. Which part exactly? The top? What top? Okay. You're welcome. All right, guys. So let me wait one more minute, and then we're going to start about talking other classifiers from scikit-learn. All right, so let's start now. So Steve went over about all the metrics to evaluate the model and how to create the body when inserted, but
So what you could do now, can you guys hear me? What you could do now, Shizota, is you've got that alone variable. You can just include that in the features, maybe along with class and sex. And then you can just copy. So if you have features equals p class sex alone, and then you can just copy the rest of the code. You could subset your data frame to features, do the train test split, fit the model, and then check the accuracy score just like we did in the original data frame, and that would work. Let us know how it goes.
okay. So let's start this now. So what is overfitting and underfitting? So this is a really important topic, especially when you're building a machine learning model. So let's first describe what is underfitting. Underfitting is when the model is not actually learning by the data you're giving it to. That means perhaps it doesn't have as many parameters as should have. And yeah, so overfitting is the opposite. Overfitting means that on the training side, the model has learned everything. Actually, it hasn't learned everything, has memorized everything. Like you can see the difference here. Like let's say, for example, we have two groups. You want to predict the groups, and you see how the red line goes in the between the boundary of the circles and the edges. So basically, the model memorize the actual path of, I mean, every position of the actual class. And ideally, this is what you want. You want something that learn from the training data, and it can generalize from unseen data. Like it can make predictions from data that haven't seen before. So, let's say, for example, like it can accept a few errors like this one. It's been misclassified, but because it's you can say is within the neighborhood of the circles. So what is underfitting and overfitting? One good way to represent this is understanding how the error changes between the training and the testing. Let's say, for example, this is the amount of features you have. Like, let's say in this case, if you increase the number of features from two, like from the class and sets, and you keep adding, so you might overfit your model because meaning that the model has learned something, but maybe another column is bringing some noise into the model that the model doesn't really generalize, and it gets confused. So let's say, for example, this is the training, the error in the training set, and as you increase the parameters, the error keeps reducing and reducing and reducing. That means it is memorizing everything. But then when you test it, this is the testing part. It overshoots. Like, let's say if you have 15 columns, for example, and actually it's a small sample, but let's say if you have 15 columns and those 15 columns are overfitting your model, then the error in the testing set is going to be huge. This one here compared to the training set. So ideally, what you want is that the error between the testing and the training must be similar. Like, this is the optimum part. So that means that the model has really learned from the training data and can generalize on scene data. I also have the link here of this article where I got the images from. I highly recommend that you go through over it so it can give you a better picture of what underfitting and overfitting is. So now, one of the models that was included was decision tree learning, and there are other models as well. We didn't include the how those models learn because we want you to go and learn it by yourself. But I'll explain how the decision trees learn. So let's take this example. Let's say, for example, that you want to go out. So a decision tree is basically they ask questions. Like, is you ask one question, and then based on your answer, you move on to the other question. Let's say, for example, if you want to go out and you ask yourself, oh, do I have work to do? If the answer is yes, that means, oh, and I'm going to stay. If I have nothing to do, then the answer is no. So I should see how it is outside. Like, let's say, for example, we don't have like the pandemic we have right now, and then you look outside and see if it is sunny, and if it is sunny, you go to the beach if it is in the summer. But if it's not sunny, you can go jogging maybe, or if it is raining, you can call your friend and maybe go to the movies or to the park. But I guess that really explains how decision tree learns. So I know some of you tried other models in the practice. So for this one, you see here, this is a data set. So for simplicity, we're going to use only two columns, which is the class, and actually let me set here, class and the sets, and split it. You have the decision tree classifier, and I added the Gini criterion here because basically that's what decides how the decision tree is going to learn. Like, you have different criterions. If you have more questions, I can, like, about what parameters does the models have, or you can ask the question to the notebook itself. You see, by default, you use the criterion uses Gini, and you can play with the parameters of the model, like the splitter, like how depth you want the model, the actual tree to go on, like how many leaves, and the minimum examples before it divides into another question. But yeah, let's move on. So here we train the model. Let's see how decision tree learns. We check the score, which is 78. It's very similar to logistic regression. And yeah, I have one question for you guys. So after I explained the underfitting and overfitting, what do you think about the outcome of the training and testing set in terms of the accuracy that I got? Is it overfitting, underfitting? No one? Appropriate fitting? Why? Yeah, but why? Yeah, that's good. The numbers are very similar. And let's say if I change the instead of sets, I have pair. Initialize again. What about now? So you're doing a train and test. So you never overfit, right? I mean, I didn't have to do this. Well, I have to do the split again because the number of the features change. But so Marina says underfitting. Why is underfitting? Anyone else?
Oh, so there is a correlation between those two columns, the fair and the class.
Yeah.
So it's kind of like, oh, maybe it's overfitting. I don't know. It's like the same. You fit in the same data twice.
It is overfitting. So
yeah. Okay.
Something I did explain just to visualize it better. If the accuracy of the training is higher than the accuracy of the testing, that means it's overfitting, which is in this region here. You see the error of the training set is very small compared to the error of the testing set. If it is underfitting, it will be this region here, where the error don't really make any sense, basically, when it underfits. All right, so let's do sets again. One of the features that you have from decision tree, and that was one question that one of the students asked before. And how do you know which columns have the more importance? So using decision tree, you can have the feature importance, and basically it's telling that sets has more importance than the actual class. As a matter of fact, let's include other columns as well and see what it says. So we have BF columns. I didn't do the, hold on, let me do the P, the dummies. Bark. All right, so let's take all the columns. I have one question for you guys. Can you see everything clearly? Or do I have to make it bigger? Okay, thank you. All right, so let's see how it does here. Whoops, it's doing better. And what about the feature importance? Okay, so can you see now how it changes? So basically the sex is the more important feature to determine if a person survive or not. And where the person embark, you can see here. One thing to notice is that everything must sum up to one, which is in percentage. And yeah, let's check the how good the model is. So the true positive and true negative increase compared to what we had before. And let's see how the precision, the ROC curve changes. So because there is a better accuracy, this part here, it covers increase a bit compared to what it was before. Is everything clear about decision trees? Does anyone have any questions? Okay, so I guess we can move on to another model, which is called support vector machine. So what support vector machine does, especially for classification, and is that you can control the boundary between classes. Like you see the margin here, you can control this margin, so you can basically it's like a plain get the best value that gives you the best margin based on the accuracy. And this part you can do it using this parameter, the C, or the based on the corner it has. So I don't want to go over that now because it could be a lot. We can take a whole lecture just to explain how support vector machine work. But yeah, there's a big difference between logistic regression, decision tree, and support vector machine. And I will say that support vector machine is one of the best models in classical machine learning. Well, it depends how you do it, how you use it. But let's see how it does. Let's see how can we can improve this. So we initialize the model, we train it, and see how it performs. So we got the similar score than the decision tree. Basically, the same score as the decision tree. And what about the confusion matrix? So 103 and 44, 28. Let's see. The same scores. And what about here? So precision is 0.91, very close to 1. And recall is 0.61, which is really good. Now, let's say, for example, you have different models and they're all doing pretty good. So some of the models have different errors, and maybe you can take advantage of it. And one way to take advantage is doing what I did first, which was using random forest classifier. So basically, random forest classifier has a bunch of decision trees, and when the output the label, it takes a vote on the most popular label. So let's say, for example, here we're going to use the voting classifier. This is another type of embedding machine learning models. So what you do, you specify the model. I mean, like, you have to add the name. You add the top a list of models with the name of the model. It doesn't have to be the exact name, but just for you to recognize it later on. So here what I have is the logistic regression model. Hold on, I think I didn't train it using this data, so I have to train it before having it. Okay, I'm sorry, I had to jump like this. So let's train it here. Oh, yeah. This is the logistic regression. And yeah, I have logistic regression, decision tree, and the support vector machine classifier. And the voting, it can either be soft or hard. So let's see how it does when we train it. And what about if there was an improvement? So 21. And in the testing set, so compared to what we had before, it's compared to support vector, we have the same results, basically. Yep. And for the confusion matrix, and for the ROC curve, so basically everything's the same. So now I would suggest that instead of having these three models here, I want you to practice by training the k-neighbors classifier, this model, and see how it does, if you got any improvement. Any questions from anyone? No questions? Are you guys working on the all right, so let's try this. Let me help you out. Go to this part. Okay. Say you want the gain and then so first see how many. Okay. Okay, and how do you do? Okay, k-neighbors neighbors has a lower score than any other models here. Test it. So now when we include this one, which has a lower score than most of the models here. Okay, hold on. Okay, so K and then Height parameters, they're useful if you want to know like the number you want to. All right, so let me show you this. The number of neighbors, you can change that. Like say from 2 to the number 11, for example, or 20. It all depends on which one gives you the higher accuracy, and also the weights that you want to assign to the classes. You can change that. So there are different kinds of weights. So you have weights here. Where is it? Yeah. So by default it's uniform, but you can have distance. So basically what KNN does is that when you give them the training data, it's going to learn the position of the training samples. And then when you have a testing set, it's going to classify the data based on the position that the testing samples have compared to the training data. That's why you have the distance here. In fact, KNN is also used like when they want to interpolate values. Let's say for example, if you measure the temperature on one side, and like in the Bronx, and you measure the temperature in Brooklyn, you can use a KNN to determine the temperature in Manhattan because it uses the distance. Any questions, guys? So let me comment this out. Oh, yeah, I didn't finish this part here. So what happens when we add the KNN? So no improvements. Thank you. So basically it stayed the same. So if that happens to you, then I will recommend not to include model. And what happens when we do boarding soft? Okay. So boarding soft is when you want to predict like basically the probability of being that class. The models that I have here, logistic regression and decision tree, doesn't give you the class. Support vector machine does. It gives you like the probability of this sample belonging to this class. In this case, we should use the hard boarding. All right. Has anyone tried playing with the parameters of any of the models? I mean, hyperparameters. I mean, we can play, let's say, for example, K&M. Let's say we want the n neighbors to be what? Two, for example. See how it changes. Yeah, we got a better score by changing the number of neighbors. What happens if it is 3? Nah. So 2 is good. So Tyrone, Which hyperparameters have you played with? Okay, and all right, so let me show you this, another hyperparameter that, let's say, if we want this number to be, the C value to be 10, what happens to the performance? Stays the same. And if it is 100, stays the same. And what happens if we change the kernel to be linear? Let's see how we change. You know, the confusion made, yeah. Let's do RBF. So yeah, that's true. Actually, K&M, they call it the slow learner because it goes for every sample in the training set and learn the position. Okay. Quick question: Who's behind? Who's having issues with Also, now that I hear this question, what are some useful K&N hyperparameters? There is one method to evaluate K&M, and it's called the elbow method, where you implement different neighbors and see how it changes. So let me send you a link so that way you can see elbow method. You a better understanding. Yeah. So I guess at this point, you know why they call it the elbow method. So a C parameter is like you can control the boundary here, the C parameter, like how big you want it. Basically, what it does is it penalizes the based on the weights. Good question, Tehran. You guys want to play with the decision tree and see how it changes? Let's try decision tree. Anyone? Okay, let's say for example, decision tree. What can we play with? Let's see. Okay, max def 10. About 5. Oh, it stays the same. B. Okay. And what? Minimal samples to split. Setting instead of 2, make it 4. There's no more change. Oh, something that I didn't mention is that every time you're training a model, it's good to specify the random state. So I have 42 here, But what this means is that the random state, you have a random number generator. So basically that determines what the weights are going to be of the actual model based on what it's been learning. And when you specify the random state, what you're doing is that you're making your work reproducible, meaning that it doesn't matter how many times you run it, it's going to run basically the same numbers, even the same predictions, if you specify the random state. If you don't, then you can have, I mean, the training is going to be different every time. So basically, it's like making work reproducible, and that's what you want at the end of the day. Let's say, for example, if you have a model predicting, if you have a model on the cloud predicting house prices, and then for some reason you have to go back and check your work, and then now the model is acting differently. So maybe you didn't specify the random state. So that's why you want to be aware of that. Any questions, guys? Steve.
Tyron had a question about using entropy versus I've never even said this out loud. Do you say Guinea or Genie or Gini?
Guinea.
However you say it, Guinea.
Yeah.
So I know that entropy uses like Shannon entropy, which is like, like if you flip a coin, is your entropy 1, I think, right? And so it looks at where you split to get the biggest like reduction in entropy to get the most information gain, and that's how it calculates the splits in the decision tree. I actually don't know what Guinea uses. Yeah. Do you know, Carlos?
About Guinea, I forgot how it does it. I can show you right away, like the actual math behind. Hold on.
That's exactly right, Mike. Yep. And so the idea is that if, like, in the node of your decision tree, yep, you've got the right intuition. And so you want to have a node of your decision tree be uniform, or at the very least have like big majority of one class, and then it would have a low entropy.
Also a good one. Decision tree. Okay. And then I can give you the link, but yeah, this is explaining the whole math behind the Guinea entropy. And let me share this here in case if you guys want to dig into it.
You can always try both and see which one has better accuracy is what I would do. Any final thoughts, Carlos, or any closing questions from you guys?
I'm good. What about the students?
Cool. Well, yeah, this was a heavy on the lecture to just kind of dump a bunch of information about how we think about these frameworks for machine learning and kind of the process of doing the train test split, trying different models, doing some feature engineering, evaluating the models based on the changes that we're making. So hopefully that gave you a good sense of how that works. And yeah, like we said, going forward, expect us to post some things in the Slack for you guys to prepare for class That way we can use class time more for either working on projects or having you guys actually work through some examples and having us help you. So yeah, this was kind of, I think, the last sort of introductory lecture, and we should be transitioning a little bit. Let me check the chat.
Hold on. Tyrone has a good question. Any method that picks the best hyperparameter for us? No, you have to play with it. You're the one who picks the hyperparameters.
You can look up grid search, but it takes a lot of time, and I've never actually really leaned too heavily into that. So
actually, now that you mentioned this, I think we want to use grid search next week. So next week we're going to do regression problems. So the whole idea is to walk you through how to actually create a model and then like all the process from A to Z. And yeah, so basically what you learned today was machine learning models for classification. But next week, since it's regression, I would say regression in a sense is more intuitive than classification. Yeah, so we want to basically teach you all the protocols that you have to follow to create the best model. Anything else, Steve?
I think that's good. Look for some email and a Slack post from us about next steps you can get started on your project. Drop in on our office hours if you have any questions about the material or your project. And yeah, we'll see you guys next week. Thanks for stopping in. Oh, yeah. Nassan's got a quick question. Go for it, Nassan.
Yeah, my question is, you said we're going to start transitioning starting next week. So, like, transitioning to what? What exactly do you mean by transitioning?
Next week, I'm sorry. Go ahead, Steve.
No, you go ahead.
So next week, we're doing regression.
And I just meant, Nassan, that we'll put a little bit in Slack, like we might put a video or something to read in Slack that maybe we would have presented in class so that we can use that class time as time to work on projects or a time for you guys to practice coding some more, like more complex projects that we would be able to help you out on. So we're just transitioning from a more lecture-based video call to a more project and example-based video call, if that makes sense. Cool. See you next week.